Okay, I think we'll get started. I think we're waiting for a couple more people, but it is 10 o'clock. So welcome to this introduction to GPU programming using HIP. This is a 3-day course. I should show my screen, which should be too much slides. So this will cover a number of topics. First things first, has everyone been able to access ARCHER2? I know there's a number of people from the ARCHER2 team here, but there are also a number of potentially new people. You should be able to have got access instructions in advance of the course. You'll need to set up an account safe. You'll need to supply an SSH key, and you'll need to use a multi-factor authentication pad in order to access ARCHER2 once you're logged in. If you have any issues setting this up, please message in the chat, send a query into the safe, and we will try and help you out from there. Please ask questions throughout, and if you have any issues with this, do let us know. Please try and test this now if you have a moment to make sure that you can get access. So during the course, we'll have the chat on here to use, but sometimes that can scroll past and we can lose track. If you have persistent questions as part of the ARCHER2 GPU programming page for this course, there's a course chat. The materials are also linked here if you lose track at any point, so please find them there. This course chat is an Etherpad which allows you to write notes and they persist and they highlight based on different people. So that way we can pick up questions later if we don't have time during the flow of a particular session. So please make sure you use that if you have anything you want to ask. Okay, that's a bit about prep. So now a bit of introduction about the course. So this is organized as a 3-day course. It used to be 2 days, and we had some feedback from when we ran this in April that it was a bit too compressed. I have a concern now it's maybe a little bit too long for the content, but we will try it in this format and we will see how it goes. So I suspect we may be finishing a little bit earlier today than maybe we planned, but we'll see how the flow of the content goes. So some of the learning outcomes we plan for this course is kind of have a broad understanding of why GPUs can offer an advantage over CPUs for performance. So how to move data between hosts and devices between the CPU and GPU. Now how to write a kernel, how to run the code on an accelerator. To understand why occupancy on the GPU is important and why this helps drive performance on the GPU. We'll try to introduce some of the various types of memory spaces you can access and use on the GPU hardware, and get you some practical experience implementing kernels and collections of kernels, so streams and graphs. This is where, when we've run this in the past, we didn't quite have enough time, so we're going to have a little bit more space to talk about streams and graphs because they're kind of complicated, and we ended up with a bit more of a ramp up than I think we would have liked last time. Okay, so topics, it's kind of just covering the same really, but we're going to start with looking at performance models and graphics processors. We'll then discuss the CUDA HIP programming model, and we'll become very clear that actually these are pretty much equivalent via some vast and minor differences. But we're going to talk about HIP because we have AMD GPUs on ARCHER2. We're going to talk a bit about memory management, as I said, moving data from host device and where it's kept and how it's kept, executing kernels, and some performance considerations. We'll then move on to different types of memory, managed, shared, and constant. And this is around how much control you want over who has, how much you want to leave the control of where the memory in your data is stored. Yes, all the lectures are recorded. They will be put up onto the training page where the content is linked and advertised, and it will be archived forevermore. Sorry, where was I? Memory. Managed memory, shared memory, constant memory. We will discuss managed memory is around letting the runtime do most of this for you. You let it decide when it needs to move data between the host and the device. This can mean that you have an easy time programming because you kind of leave the runtime to decide this and you manage it less, but ultimately this kind of performance implications which you may not want. Shared memory talks about memory that can be shared between threads, and constant memory is some read-only memory that's available. Then the more kind of complex topics around streams and graphs. Streams, all kernels that we're going to, pieces of code that we're going to run on the GPU are going to enter into a stream. And streams are ordered, but you can have multiple of them. So how do you orchestrate multiple streams? What are the considerations there? And then finally, graphs. How do we manage dependencies between different kernels and different memory move operations? And can we organize these into a structure? And then a little bit on device management, and we try to wrap this up with an example, as a country grading example. That'll be most of the final afternoon is the idea for that. Okay, so this is kind of the schedule as I've kind of discussed the topics. It's these kind of things here. We will try to take regular breaks. As I was saying, I think we're going to be slightly earlier. I think the schedule's, having reviewed the content yesterday again, I think we're probably going to finish probably around 3 o'clock today, because I think we're going to have to move the programming memory management session that's sort of just meant to be after lunch into later this morning. Otherwise, we'll be having a very long lunch. But that's fine. What we want to make sure is then there's more time in the afternoon then to sort of go through some of the performance considerations work, because this kind of afternoon section around kernels and looking at some of those performance considerations are the key thing to take away from this, really. Each morning then for the subsequent 2 days, we're just going to do a brief overview of the day before, where we'll look at some of the examples and some of the solutions and have a bit of a discussion before moving on to the next topic. Hopefully that means there's enough time to ask questions and nobody feels rushed through the content. But to start this morning, I've got some slides just to discuss some key topics. So we're going to start on performance models and graphics processors, and then we'll talk a little bit about the programming model. Where to find additional information, right? There's loads of things out there on the internet for this. These are some sources of useful documentation, especially for this course. And more widely, we're going to focus and talk about AMD a lot. I am going to refer to some NVIDIA documentation because they have some good stuff now and again, because the principles are the same, really. So if you suddenly see a very green looking diagram, then you know where they've come from. So the course materials are linked on the website, and the ARCHER2 documentation. There is a user guide for the GPU partition. You will see diagrams and stuff from there I've nabbed for this talk, but please refer to if you're having issues with things like Slurm, and if you have problems, do put a message in the chat, but there's a lot of good information there. More generally, there's documentation on the NVIDIA website about HIP. And if you want 2 good talks about the principles of GPU programming, these 2 GTC talks from NVIDIA are very good. They're both by Stephen Jones. They sort of discuss some of the fundamentals about why you design a processor in the way that GPUs are designed, and why that offers benefits, and some of the physical limitations that you'll put up against in that. This is a very nice professionally given talk, and it looks very good, lots of graphics. So if you want another reference to, if you're struggling with the concept, these are good places to go. Okay, compute performance and graphics processors. So we're going to start with a very simple model of performance on a computer. You might have, so we can think about it very simply as just having a processor and some memory and the movement of data in and out of the processor to do operations on some data. If we take this simplified model, there can be a number of considerations for performance. So clock speed, the rate of the issue of instructions by the processor, memory latency, the time taken to retrieve data items from memory, memory bandwidth, the amount of data transferred in a unit of time to the processor. And then we can consider parallelism. Can we replicate the basic unit, this processor memory model, in order to do more total operations in a given time frame? Okay. And this is a very, very basic but good description of how processors are generally designed and some of the limitations. So the reason we're going to go through this is to discuss what the limitations are on CPUs, and we can try to just look at why the design changes for GPUs might give us an advantage. And once we've established sort of what the general design is, we can discuss how we're going to program them. So clock speed, it generally determines the fundamental rate which you can process. Okay, so traditionally, faster clock speed meant you could improve the amount of work you get done in a given time. So CPU performance up until about the early mid-2000s generally just increased because clock speeds increased. You had one very fast processor doing lots of things. Largely due to power constraints and thermal considerations, you're kind of a bit capped by physics because physics is a pain and limits you around 2 to 3 gigahertz. I think ARCHER2 runs sort of in that range around 2.8 down on the CPU nodes, 2.8 down to something like 2 gigahertz. It's pretty standard. As we'll see, GPUs have traditionally had slightly lower clock frequencies, but about just under 2 now. So without some unforeseen sort of breakthrough in how we deal with clock speeds, what the tendency has been to is then after this sort of limit came in the mid-2000s, we started to see this number of logical cores in a given processor increase. And you can kind of see what we'll discuss around GPUs is kind of the extension of that further, having lots of cores opposed to just tens. Okay, so the other consideration is memory latency. If it takes you a number of clock cycles from a standing start to retrieve a piece of data from memory, you're going to be waiting during those clock cycles and not doing useful operations. So you'll either do some clever overlapping or have some work to do and send the instruction to retrieve in advance, or you're going to sit there and waste cycles. CPUs try to mitigate this by having some layers of caches, so there's memory close to the processor, thereby reducing the access time. You have many caches in a hierarchy, and the closer to the processor, the smaller the cache, and the number of bytes, but the faster it is to access. So you end up with this nice thing. You'll see that GPUs don't have this same level of hierarchy that you do in CPUs. But a quick exercise to make sure you can log into ARCHER2 and also make sure you can see this yourselves. Could you just spend a couple of minutes running the ls CPU command on one of the ARCHER2 login nodes and just seeing what results you get back? So quick login and see how that goes. If you can just, if people just put something like say they completed in the chat when you're done, I'll know to move on when I see quite a lot of people have done that. It looks like most people are getting through that relatively quickly. So yes, so this is the result I've got. So yes, you can see you've got some level 1 cache, and then you've got some shared level 2 cache. Sorry, some level 2 cache, and then you have a shared level 3 cache for low number of instances, forming some form of hierarchy. So, a couple of questions there. Someone's having an issue with TTOTP. So if you're trying to log in and you're having issues with that, that means you need to set up a second factor authentication. So there is some documentation on the website. So I think if one is around, could you just post a link to how to set up MFA? The point there is that you'll have a numeric token that will get generated. You'll have to scan a QR code on safe. It will set up a using an MFA agent and provide you with the code back. And now you'll need to use that to log in to ARCHER2. Okay, so we have these complex hierarchies in order to try and smooth out the memory latency. This is really important concept because the way that GPUs differ majorly from CPUs is that while a CPU will try and smooth out this latency curve, the GPU tries to hide it. So you'll often hear that GPUs are described as latency hiding machines, but they'll switch out blocks of operation for things that are ready to take over if there's something that's going to cause latency, and therefore hide this by having lots of work to do, and able to move things so useful stuff's always getting complete, even if we're waiting for some memory, and the latency is going to cause us waiting. Okay. What is a socket? Someone asks. On one of the ARCHER2 blades, you have 2 CPU sockets, each with a separate CPU device in them, and each device has 64 cores. So you have 2 socket machines. Usual sort of desktop or laptop will just have one. But that's what you have 2 different sockets. Okay. Next consideration for memory bandwidth. GPUs generally have quantity DRAM. DRAM is expensive. We have to get it to be fast, to get it to be large. It costs a lot of money, and it likes to break eventually. While the overall size can vary, you will usually have order of hundreds of gigabytes worth of space. So ARCHER2's standard CPU nodes are 256 gigabytes. There's some high memory nodes which are 512 gigabytes of RAM per node. The memory bandwidth speed for these is usually on the order of 100 gigabytes per second. Many real applications are actually limited by this more than they are the pure flops they can get at. So this is why I have this roofline plot on the right-hand side that basically says you have 2 limits, which is your peak rate which you can do operation, peak flops. So if I change my CPU frequency, I may be able to do more flops, move this up and down depending on if I increase or decrease the processor frequency. But really, getting data in to the processor is what's restricting you. And what GPUs tend to focus on is improving the bandwidth, the rate at which you can get memory into process, and then affect. So you're of the order of thousands of gigabytes a second in terms of memory bandwidth from very high rate GPU memory. That has an implication on the way that you program GPUs. So that would move this diagonal sort of bandwidth bar up, across the cell and allow you to access, not be less limited by bandwidth, or move the point which you're limited by bandwidth up, therefore allows you to get improved performance. And this can be quite impressive. So memory bandwidth is a crucial consideration, which often people don't think it's being a limitation. So profile your codes. And then parallelism. So finally, what's not possible to increase the clock speed for the introductory processor, we can just start duplicating processors across the CPU, and now we have many hundreds of cores, or 100-ish cores per node, and it's quite common. ARCHER2 is 128 cores per node, as I discussed. With hyperthreads, this is 256, but you tend not to want to use hyperthreads. You can also see information about how these cores are arranged from LS CPU. So here I have the output. Here you can do it for yourselves, but you end up with, okay, this is done including hyperthreading, hence why we've gone up to 256, but just halve it. And you have NUMA regions. So then you start having to organize. You can go to more cores, but you start having to organize them into blocks with some shared sections of the cache in each of the blocks, making the organization of the cores more complex and the memory organization a bit more complex. But this is quite common in modern CPUs. AMD has gone for this kind of chiplet design, which has these bigger NUMA effects. Intel's traditionally kept sort of monolithic dies, but they've all sort of tending to this sort of chiplet design now with Intel's newer CPUs. So that's one way you can improve performance, but this has limitations. Because you've not actually solved, if your fundamental problem is getting memory in, this doesn't solve that issue necessarily. It just generates, gives you more processors with the same limitation. Okay, so finally, graphics processors, the thing you came here to hear about. Ultimately, the introduction of graphics processors was sort of driven by commercial interest. Generally, is the way we have to operate in HPC. We don't have a ton of funding to design bespoke hardware and run and build large quantities at scale. We tend to be driven by what the market does. They're subject to exactly the same considerations as we've just discussed. The hardware design choices resolve them differently, and started out by trying to solve the values of pixels and screens concurrently because they're entirely independent work. The clock speeds, as I mentioned, have traditionally lagged behind, but are now broadly similar. The difference currently, I think the latest generation hoppers is something like 1.9 gigahertz, whereas the ARCHER2 CPU is running at 2 point something. So they're not that far behind anymore. So yeah, your memory latency is not gone away, but the mechanism used to mitigate to allow very fast switching between parallel tasks. This sort of eliminates kind of the idle time. So we'll discuss this a lot, and this is really kind of one of the key takeaways is that you must provide your GPU with a lot of work so it can do this switching automatically for you. You don't need to manage it, but you need to tell it you have independent work it can do, and it's available, and it should go and do it. And then it will manage the fact that if something gets stalled, it will quickly swap other extra work in to start moving forward. And that way you keep very high performance sustained on your GPU. Yeah, so GPUs typically include high bandwidth memory, very small capacity. So this is order of 10 gigabytes. So, but again, this is a little bit old, this slide. So the Cirrus GPUs, for example, V100s, sort of 2017, 2018 vintage, were 16 to 32 gigabytes. The next generation from NVIDIA A100s were 40 gigabytes and then 80 gigabytes. So that was the last few years. And now hoppers are 96 gigabytes. So we're order of 100 already. I think the latest AMD offering, the MI300s, is something well over like 150 or something. So we're less limited by the total memory available on your GPU that you it's now getting up towards the size of a CPU node that we'd see on ARCHER2. Remember, ARCHER2 is only from sort of like 2020, 2021, so it's not exactly old technology either. So GPUs have been really designed specifically to solve the parallel problem of rendering pixels. So they have thousands of cores to do this independently, and we're going to take advantage of this in order to do useful science opposed to rendering games, however different levels of usage you may think these two things have. The way these are organized, so obviously it's been a while since we've used sort of texture buffers and things like this to do scientific compute. We no longer need to hijack the existing sort of design. So the designs for graphic processors directly, no, we have more dedicated designs. We take the same principles. And the way the hardware is organized, and that's diagrammed after this on this very texty slide. So the cores on AMD GPUs are organized into what's referred to as compute units. And if you use the CUDA program, we obtain a CUDA program, this is your stream multiprocessor equivalent. I've tried to keep a little glossary below of equivalence here because of the jargon difference, but the principles and what they do is very similar. So each compute unit contains several smaller processors called stream processors in AMD's language. These processes are responsible for carrying out the mathematics operations that are required for tasks such as rendering graphics and video, or more importantly, performing scientific calculations, or navigating or doing machine learning or whatever else. Okay, so we're going to look at AMD MI210s during this course. That's what's on ARCHER2. They have 104 compute units. Each compute unit houses 64 stream processors. So you have a total of 6,000 stream processors working in tandem. So again, you've got a way of increasing the total number of processors by an order of magnitude more than you had on a CPU. They can't do complex operations. They're going to be terrible at switching. They don't switch context very well at all. They're not very good at dealing with branching, but they are excellent at doing lots of work in parallel and working in teams on a single instruction. So even though you sacrifice clock speed, you're still going to get a performance benefit. So okay, as I said, I'll leave this. So there's a link here to more details about AMD GPUs, and I've got some more links related to the hardware if you want to look at the details of that particular technology. There's a little glossary here about how to translate between different vendors' jargon, because I always find this maddening that they effectively borrow everything else, but they've decided to come up with their own terms for most things. Okay, so what does a stream multiprocessor look like? So this is something I have borrowed from one of these nice talks that Stephen Jones has given. To give a little bit of a diagram of what in this case, a stream multiprocessor or equivalent of a compute unit looks like. So you have some L1 instruction cache that's shared amongst all these different threads. You have multiple different warps. And a warp is a group or collection of stream processors. In the AMD language, this is a wave front. I've got my words right. That do the same operation on multiple bits of data. So each thread gets a different piece of data, but they do the same thing on the data. And this is what drives the programming model, really. It's around this decision to say you're going to do the same instructions on an independent processors are going to take these up. This means you need to make sure that every single thread should be doing the same thing at the same time, and that causes limitations. So you have a total number of threads that can be active on a stream multiprocessor time, and then we'll talk about what blocks are in a bit. You have a total number of threads that are able to, total number of processors which are active on each warp. This is set by hardware. There's a number of different groups of these threads that can be active at any one time, which means this is this swapping in and out. So one may be active, something needs to wait for something, another one could go active and use the calls effectively. And then you have small amounts of cache. Okay, so you have kilobytes worth of L1 cache here, but you have very high bandwidth to load. Okay, this is the previous A100 generation, so your clock speed is down a little bit. It's 1.4 megahertz at the fastest. So what does this look like when you now scale this up to a GPU? This is a diagram from AMD's documentation. You then have a large collection of these compute units organized together. So we said 104, and they have some memory associated with them, but a lot of their cache is away from the compute units itself. They have some instruction cache locally, but other caches are further away, and this is where you start to see differences to CPUs. Then some of the caches are less associated with the core itself and moving data around, but you have the ability to move data in at speed is there instead. So you have a program counter for each compute unit. You have a little bit of local shared data on each compute unit that allows you to share some information between threads, streaming processors which are running. You have some constant cache which you can read from. And then this unit is replicated multiple times. So that's what I was going to get. So we'll talk about how different GPUs will replicate these blocks differently. So for AMD, for example, the MI210s that we have in ARCHER2 have one of these blocks per GPU. But if you were to go to somewhere like Frontier or Lumi, so Frontier is the current fastest machine in the world, the Oak Ridge, has two of these per GPU organized together. So these end up being, these groups end up being building blocks for larger processing units. Okay, we talked a little bit about what makes up a GPU, why they're a little bit different, and how they're structured. If we now look at the host device picture, what do I mean by this? I mean, how do I then couple a GPU to a CPU? How is the hardware organized? What are the speeds and feeds between them? So I never have a GPU just kind of on its own. That's not a whole node. I need some CPU there to kind of help with orchestration of the GPU's activities. So in this context, the CPU is often referred to as the host, the GPU is often referred to as the device, and they both have memory. So whereas a CPU I have, I'm able to deal with additionals much more effectively. I have a small number of cores, but I have lots of memory. I then usually have a bottleneck. I have a very small speed to be able to get between the CPU and the GPU. I then have a reasonable sized memory on the GPU, but a very fast way to move data into the GPU from that memory. And often the first thing we're going to discuss when we do a little bit of programming is this transfer of data between the CPU and the GPU, a little bit about how the CPU is orchestrating the operations of the GPU. And in modern configurations of the hardware, you'll often see nodes with 4 or 8 GPU devices and a couple of, well, maybe 1 or 2 CPUs associated with them. So this is a sort of schematic of the ARCHER2 nodes you can get access to. So this is a 4 GPU per node. There's only 1 CPU. You will have access via the Slurm scheduler. There are some example submission scripts in the docs as we do examples. You will need to add an account when you submit to those. There are no GPUs on the login nodes, so if you're expecting there to be some, there are not. And if you have compile time errors related to that, you shouldn't, because the system should be set up to be able to compile the login nodes without much more than a couple of warnings. But you may see that if you try to compile code in other locations, you'll often get asked, cannot detect runtime or so on and so forth. It's because it's usually expecting the drivers related to the GPU to be accessible. So just be wary, that's quite a common issue when you're trying to compile your own code. Another thing to mention, just for general consideration of performance, is that this setup of having a node with multiple GPUs, and then you have very fast connections between the GPUs themselves. So we're not going to really discuss this in any detail, but I think it's important to make the point that the design is such that these extra GMI, these blue links, are very quick. It's then slower to go out to the CPU. So, and what you'll see between different hardware vendors and designs is that the external networking can then sit close to the GPUs. So the Tersa system we have, Dirac, we operate for Dirac, has very fast GPU interfaces, network interfaces on the GPUs themselves, which means you don't ever have to switch the CPU to speak to the network and other nodes and start to scale. But the speeds of these GPU to GPU communication can be very quick, up to something like 600 to 900 gigabits per second. So you really can start to scale very nicely. We have a very limited number of these nodes, so you'll be sharing them. So you'll be applying for access to a single GPU at a time. Question in the chat: does the GPU connect to a hard disk for saving output, or need to connect to the hard disk driver through the GPU? I'm curious if we have send data directly to the hard disk. No, so you have access to a file system via the CPU and these network interfaces. So what you do is you'd have to copy data back from the GPU to the CPU memory, and then you'd probably call a standard I/O function from there. There are a couple of exceptions because there always is. I think it's GPU Direct I/O from NVIDIA allows basically a pass-through, so you can read and write directly to the GPU memory. I've not used it. I've just read a little bit about it. So there are fun things you can do that way. How much it actually saves you, I'm not sure, because commonly your limitation size of problem you're putting in a node, if you're running at that scale, is the CPU memory about what you can store. And then you try to be clever about the information you move to the GPU to do operations. And a lot of your effort as a programmer is to make sure that you minimize the data movement. Now, you can choose to say, well, the size of the simulation I'm going to do is the maximum sizing of GPU memory, but you're leaving a lot of CPU memory and capacity on the table by doing that. So thinking about ways you can get information and overlap computation and data movement is important. We're not going to discuss a lot of that detail here. I just think it's important to flag. Okay, just before finish up this session, so we are going to submit jobs from the ARCHER2 login nodes. Select the GPU-shared option, SHD shared option. There's too many people here for everyone to get their own node. We've only got a finite number of nodes on the system. And what we're going to be doing is looking at the fundamentals of GPU programming, I think there's a little bit of discussion on the last day around device management and how you might think about passing information between nodes. But there are hopefully good interfaces to using MPI with GPUs as well. So, but that fundamentally is an MPI discussion. We won't go into that detail here. I think there are plans to either update the existing MPI course or include some more information in a separate session around GPU and MPI. There's documentation on the ARCHER2 docs about how to compile for GPU-enabled MPI, and some considerations there, but we won't discuss it. But if you're going to use exclusive nodes, we've limited people later to people can have access to up to 2 of them. This is to allow fair share in the system. And you will be limited. So when you don't need to allocate a lot of things when you're setting up scripts on these nodes. The CPU core count is just, and the GPU and the CPU memory are just evenly divided between users, so that everyone gets a fraction of the CPU and a fraction of the memory allocation equal to the fraction of GPUs they've asked for. So once you've got your resources allocated, you just can run srun and set the number of tasks, MPI processors that you're going to want. The answer is 1. We don't think we'll be doing more than that. If you're finding yourself having to wait a little bit, it's probably because there's 30 of you and there's going to be 16 GPUs available. We haven't got a reservation. We'll just be using queues, so try to be patient if this takes a moment to run. But you should be able to do compilation stuff on the login nodes. Right, okay. Just to finish off, before we'll take a break in a few minutes, I just wanted to kind of highlight the GPU hardware landscape and some of the other software landscapes, just so you're aware of what else is out there. I've just provided links here to a number of different GPU products that are kind of either available or latest, or kind of the current generation and the next. So we're starting at the top, MI210s. The 250s and 250X is what you see in the very large GPU-focused systems in the US and in Europe. The 300 series, which we have a diagram on the top right, is what you're now starting to see as the next generation of hardware available from AMD, and these are looking very competitive in terms of what they can offer. They have an A and an X model. The X model is just everything's GPU on a single GPU. The A is what I've got a diagram in the top right. This starts to combine the CPU and the GPU onto the same module. So this tries to remove some of that host-to-device movement that we're going to really focus on here. How successful this will be in practice, it's not yet clear. I don't think anyone's got their hands on this very much yet. There's been a couple of demonstration accesses, but nothing more. The idea is that this transfer of data between the CPU and the GPU is often very limiting. It also makes the programming complexity slightly harder because you can't leave it so much to the runtime to deal with the movement because it's quite costly. The equivalent of NVIDIA is on places like Cirrus for V100s, which are now getting a little bit old, A100s, which were the last couple of years, and the brand new sort of things are the H100 and the Grace Hoppers. The Grace Hopper is a similar type of system to what the AMI 300A is trying to do, is now starting to couple the CPU and GPU much more closely onto a single board to use the way you move data between them. But really, as you can see, the direction is trying to minimize this data movement bit, and that's what we're going to discuss data movement first today. But it's very important to consider that when you organize your programs. Intel also does GPUs now. I don't know very much about what Intel offers, I have to admit, so I'm not going to go into a lot of detail. The main thing we know about them is that Aurora has had a slightly troubled. Aurora is the large GPU-based system at, he always forgets what this is. Argonne? No. Yes, Argonne. And so there's now an offering from Intel as well, and they all use different, the next bit, programming sort of interfaces, APIs, and landscapes. So we're going to focus on talking about HIP, which can be then target either AMD ROCm devices or NVIDIA CUDA devices, which offers a little bit of portability, but you may be limited about what you can do because HIP's always kind of behind CUDA. So if you really want some fancy new functionality in the latest release, you may not be able to access that via HIP. The point to say here is that what we're going to discuss is part of a kind of continuum of level of control that you can access versus portability. And you have everything from the top left. I have not included actually my little list on the right. C++ standard parallelism, which allows you to use elements of the standard parallels to then execute on devices and then do operations on accelerators, GPUs. OpenMP offload is another option that allows you to target accelerator devices. OpenACC was kind of a standard to start doing this. Kind of got a little bit ahead of OpenMP, but OpenMP is kind of sort of catching up now, and this OpenACC initiative, I think, still being pursued by NVIDIA and AMD and the like, but maybe has less of the community there because a lot of people have been using OpenMP for so long. Cocos and Raja are two APIs which came out of the exascale computing project in the US. They offer their own ways to go about their own interfaces to try and be more portable. That's kind of more of their focus, to look at being able to target multiple different hardwares. You didn't want to end up sort of vendor locked, so your procurement of HPC systems is entirely dependent on one vendor. That's a bad place to be. So there was investment to build both these out. They are still live after the end of the ECP project, and they have a number of tools which are supporting them around profiling and debugging and things like this, and understanding memory. Then you have SYCL, which is there's an OpenSYCL standard, and there's OpenSYCL, which there is a group that support an implementation. There's also as part of one API for Intel. There's a company just I think near Edinburgh called CodePlay, which worked on this for a while, but are now part of Intel's organization. There is some targeting to other devices that aren't Intel here, but again, the portability is more limited. The point to say is you'll come across lots of different abstractions, but the fundamental principles are the same. You have a host, you have a device, they have some level of connectivity between them, and you need to manage the movement of data between the two. And by doing that, you'll be able to organize good performance. They offer different ways to manage this and different interfaces, but fundamentally they're trying to do the same operations. Just be aware that they're around there. Okay, and finally, the level of support for these different interfaces changes depending on the different hardware vendor you're targeting. So this is a very nice paper a nice figure from a paper that discusses the level of support across programming languages and different hardware vendors. So obviously we're going to talk about HIP here. It's very well supported across, relatively to some of the other targets for C++ across different hardware vendors. CUDA's obviously been a bit ahead of AMD because of NVIDIA's sort of being a bit starting this market earlier, but it's pretty much on par. But the level of Fortran support, if you're interested there, is not so much available in HIP, and that's generally across the board. Okay, surprisingly taken up much more time than I expected with this introduction. We're going to take a 10-minute break to 11, and then we will come back and I will do the introduction to the CUDA and HIP programming model. So get yourself a cup of tea, stretch your legs, and then we will come back to start that. And then once we've got to the end of there, we'll likely move on to the first example. I'm happy to answer questions during the break though. See what I love. Okay. So now we've gone through some of the general points about GPU programming, a little bit about the setup of ARCHER2, so a little bit about some of the hardware. We're now getting to that sort of the focus of the course, which is around programming for GPUs. So again, please, feel free to ask questions throughout if you have any. So the key point here is the application program does not want to have to worry about this detailed decomposition of cores and compute units in the hardware. We want to use some abstraction away from this. We need a way of describing the problem in terms of a hierarchical organization of threads of work that we're going to do. This can get kind of complicated at times with the way I find this is taught. Because it's sometimes not clear what you're talking about in terms of physical hardware and data, or the way we organize data to be passed to work units. I would try to do my best to keep this clear about what's the physical thing and what's an abstraction we've used to describe a problem. So if we have a one-dimensional problem, so an array, we can easily pass individual elements of the array to separate threads within a compute. So if you pass a group of these threads to a compute unit, the compute unit would then pass these to a wavefront, a warp, and it would execute a group of them in that particular warp. And then when they're done, the next part of it would done that one. So you then cycle through the elements in an array. So you then have the concept of a work group or a block in NVIDIA terms, or the work groups in AMD terminology. It's a collection of work items, threads, scheduled to run on a single compute unit. So in a one-dimensional array, we may divide an array up into n blocks, each block with n threads, n work items. So I think work items is much better terminology because this is data you're actually going to do operations on that need to be passed to separate threads. Wave front is then a subset of a block. and it is designed to execute in a single SIMD fashion, so a single instruction, multiple data unit. In AMD GPUs, wavefronts commonly consist of 64 threads. Okay. In NVIDIA GPUs, warps are typically 32 threads. The point here is that this is some way to a wavefront or warp. They're doing the same instruction on that number of work items. So they can do it all consistently, and then they can stream in groups of these work items to do through a block. So I'm going to pass a block or a work group to a compute unit. Then it's going to do, it has known operations it's going to do on that block. There may be other compute units doing the same instruction on different blocks of the same problem. It's going to divide that block up into groups of threads that it calls wavefronts or warps. Their instruction and that particular group of threads within a block is going to be passed to a different wavefront warp, and they're going to execute through that block in chunks. This is the bit that gets people confused about distinguishing what's physical hardware and what's grouping. In some sense, you don't really care about, in the first instance, the size of a wavefront, size of a warp. You really care about blocks and threads, or work groups and work items. Where this discussion around wavefronts and warps becomes important is there are limits on the number of different wavefronts or warps that can operate at the same time on a particular compute unit, and the amount of the size of the number of threads that can be in a given block. And these are limits in hardware. The scheduling of wavefronts to get through the work in a block is entirely managed by the compute unit. This is what can do latency hiding, because one wavefront can be operating, it hits a stall or something, another one sorting very quickly. It means you get efficient execution, and a lot of work can get done in a high latency. You need to select the number of work groups, the number of blocks, based on the problem size you have at hand. And you really want to drive a large number available at any one time, so latency hiding can be more effective. So this naturally scales into multiple dimensions. So two-dimensional problem, very obviously you now have an X and a Y coordinate. The arrangement of work groups, blocks, is referred to as the grid. This is common terminology, both AMD and CUDA do this. This is very simply for 2D, and then you have a natural extension up to 3D. Yes, and this is the key. So there's a question in the chat: can different threads work on with the same block of memory? Yes, and the point here is that it's. I think your question introduces a common misconception. In a CPU, you would go thread hardware core. You're going to have access to a section of the array, and you're going to read it. You're going to go after it contiguously. You're going to get individual bits of data in one after another and perform the same instruction in a string. Here, you don't want the same thread to get contiguous memory. You want contiguous threads to get contiguous memory. That means core 1 needs to get data bit 1, core 2 gets data bit 2, and so on, so that there's one instruction being executed by different threads on data within a block. So different threads would always in a GPU be working with the same block of data, of memory, so that they can work through on the same operations at the same time, and that drives performance. Threads they do have some shared memory that we'll get on to tomorrow that they can use to communicate or do things, but they should be working on separate bits of data so they can work at the same time. And this is why you can get branches being a problem, because if you've got your even threads doing one thing, your odd threads doing another, they have to switch in and out constantly. That's bad. So you will avoid what's called thread divergence in this model as well. You really do want them all doing the same instruction, the same print. Okay. So yes, you can extend this to multiple dimensions quite naturally, and depending on your problem, this may make a lot of sense. There are some additional limits. I think this is a little bit of the number of the depth you may be able to have in the Z direction, maybe not as deep into the number of threads. There's some limitations there, but in principle, you can still lay out your data in something that kind of makes sense to the way your data is structured. This is also why the machine learning leads itself very well to this, because it's all matrix operations which sit this model very well. Okay, so that's a little bit about how the data is organized and the program is structured. So how do we program this? So HIP, let me just answer this question before I move on. Can the map between compute units and wavefronts be established by the user, or is it automatic? You can control the size of the blocks and the number of threads in a block, and that has performance implications, but I think then the division, the size of a given wavefront is fixed in hardware. So in a sense, you can control it, but it's only with the block size, not with the warp size. There is usually a benefit to changing the block size. If it's too small, you don't have enough warps active at a time. If it's too large, then you start to run in contention with memory and making sure stuff's available. So this is a parameter you would choose about the number of threads per block, but the subsequent division, I think, is just handled by the runtime. So programming HIP is developed by ND, stands for Heterogeneous Compute Interface for Portability, which is a nice mouthful. It's a runtime API and a kernel language implemented in C++. It enables you to create applications that are portable across AMD's accelerators and CUDA devices alike. So it has some portability there, which is quite nice. HIP has two distinct types of source code, host code and device code. The host, essentially the CPU executes the host code. The code is typically C++ syntax on the host, incorporates sort of standard features. The entry point for execution is the main function. It utilizes the HIP API, and the host code facilitates tasks such as generating device buffers, managing data transfers between the host and the device, initiating the execution of device code. So that's all controlled from the host. The device, typically the GPU executes the device code. It utilizes a C-like syntax, where kernels are used to launch device code in a sense. So you encapsulate your device code in a kernel. You then launch the kernel later with a given decomposition between threads, blocks, provided at the point of kernel launch. So you can control this sizing decision at launch time. You don't need to hardcode it into your kernels. Instructions from the host are queued in streams for execution on the device. By default, you don't have to specify the stream you're executing in. By default, this will be in stream 0 and it will queue up work. There's a slight performance consideration here that if you have small blocks, so small blocks don't fully use up certain parts of the device, then there could be a packing efficiency if there's a dependency which can come in and start using spare resource. So you need to think about, can I start doing computation, and is there enough space for what's running before it to fit some of the computation of what's going to come next? And have I sized things appropriately for them to fit? Should there be dependencies? Actually, maybe they shouldn't start doing that ahead of each other. And that's what we'll discuss with graphs and stuff later. But it's important to understand that there's a queue happening on the device for execution. Okay, so compilation. We're going to use the Cray HPE wrappers for most of the work we're going to discuss, and the examples we'll see in the documentation for the course. But just to make you aware of some other utilities which you can use. So HipCC is a compiler driver utility that calls the AMD LVM compiler or NVCC, depending whether you're targeting AMD devices or NVIDIA devices, to compile HIP code. HipCC is included in the AMD ROCm software stack, so you will load a module called ROCm on ARCHER2 to get access to this and access to the other libraries and so forth. HipCC compiles both HIP code for GPU execution and non-HIP code for CPU execution. It's a wrapper, defaulting to the AMD LVM compiler for the host code. You can set different host compilers by hand with environment variables if you wish. This is quite a common thing to do. If you want to try out different combinations of host to device compilers, you can link object files accordingly. On the right, I've got some information about the different programming environments that are available on ARCHER2 for setting these environments up for you. We're going to focus on the prog env AMD setup, which sets the compiler wrappers at Fortran CC and capital CC, AMD flag, AMD clang, AMD clang++. See that on top right. There are other options, other choices you could make. There's some hybrid programming environments available to you. You can directly access these compilers yourself by typing in the relevant name of the compiler, but the wrappers make it slightly easier to give everyone a unified environment. There's a little bit of documentation below. We'll try to provide a grid that indicates what's supported by which compilers for which sort of targets. So we're, as I said, program AMD. It's going to use AMD clang++ compiler for HIP. So if you're interested in more detail, run CC. So once you've loaded the modules, I'll give you a list in a minute. Or you can run HipCC directly, and you can use management's help to get some options. You will need to compile with the -x HIP to say that you're targeting an AMD device. So you're targeting HIP code specifically to be compiled. You also find some compute capability in a second. If you want to see exactly what HipCC passes to the compiler, you can pass the verbose flag to detail all the linking and so on and so forth. This is really useful. There's an equivalent one for the documented for the Cray compilers themselves that can give you all the instructions that you've used. So what gets very complicated with GPU compiling is you're often compiling on a login node which doesn't have a GPU to then run on do some form of GPU-based compiling, which then needs to link at runtime once it's on the GPU node, and what's actually getting linked in at different times can change and can be confusing. Okay, so there's a question: is the support for Fortran with HIP on ARCHER2 likely to improve with time, or should we plan to stick to C++? This is a very active discussion. So in terms of what ARCHER2 can do, there's not libraries or compilers currently which support HIP natively in Fortran. That's not something that we have the power to implement as a service. There's ongoing discussions about the level of support provided in the community for Fortran programming very limited. kind of been driven by the ECP program in the US, looking to they've tended towards moving people towards C++ interfaces, but that's not the general operation. ARCHER2 are much more Fortran focused. I think we are planning to offer some courses more around OpenMP offload, which does have more support for Fortran, but that's still in development. I don't have any timescales for when that's likely to be. Okay. The other thing you need to be aware of when compiling for GPUs is you have the difference in what's called compute capability. Effectively, what this says is you need to tell the compiler what architecture you're targeting. And there's a number of codes that you need to, well, not a number, in AMD, there's a code that you need to pass in. This offload -arch, and they have very unhelpfully complex names. And so there's just a bunch of code to look up. There's a nice list on the LLVM docs for this, and there's also one on the AMD website. I forgot to link it. No, I did, but that's fine. So if you wonder why there's this weird architecture code that needs to be passed in, that's why. The way that NVIDIA defaults this is if you don't pass anything, it makes your binary massive by compiling for most things. NVIDIA has exactly the same setup. You have to provide a compute code. Theirs are a little bit more straightforward. They're all compute _80, 70, 80, 90, whatever I think we're on 90 now. So it's a little bit more straightforward. But we'll be using this GFX 90A. It has nothing really to do related to a particular GPU. It's more around an instruction set. Okay, I think this is my final little bit. So, or maybe one bit more. CUDA has been clearly developed by NVIDIA since about 2005. It's a bit ahead. AMD is rather late to this party and developed HIP, which kind of shadows CUDA. So, while we're going to use HIP, the key thing to remember is that you can do a bit of find and replace here. If you have an existing CUDA code, don't just go through your entire application and do find or replace. That won't work. Because there are going to be different decisions about the size, the number of threads or work streaming processors available per compute unit or stream multiprocessor. So the size of blocks, the things will have different performance implications. You need to take that into consideration. But more importantly, while HIP is trying to implement what there is in CUDA, it may only provide you with the interface and not the precise implementation underneath. So while it may be equivalent, it may not be as performant. So you may want to reorganize your code to be better. So I think, well, we'll discuss graphs because it's an important capability to allow you to organize your code. Whether this does only like sensible optimizations under the hood is going to be entirely up to the runtime. So it may, I think it's very true that HIP doesn't have quite as developed graph implementation as CUDA does. So you may find that if you're using the latest and greatest CUDA, get my words right in a minute, version, and you're trying to convert this to HIP, you're probably going to be missing some function calls which don't exist in the HIP standard at the moment. But there is a tool that at least can help you do this. So we're not going to do an exercise on this. I'll leave this something for people to look at, but I do want to make you aware of it. There is a relatively simple mapping. So there's a relatively simple tool called Hipify that allows you to try and convert CUDA code into HIP code. There are two elements to this. There's HIP examine, it's a Perl script, which sort of scans the directory where the code is you're looking to convert, and provides you a breakdown of the number of calls of different types in a particular file. And this can be quite useful to understand. Is this mainly device operations, memory operations, kernels, built-in functions? Am I doing maths operations? Am I using streams? There are some events going on, things like this. Separately, there is HIPify itself, which actively tries to convert the code for you. Some of our members at the Center of Excellence from HPE have used this. We're looking at codes for Lumi in Finland, and their sort of anecdotal thing is it's quite useful to get you started, but there is tweaking you need to do. So before I forget, in sort of the software landscape bit and the program structure, there are tools to be able to do this. Okay, quick summary, then we'll do something practical. So the goal for the programmer is to describe the problem in abstraction of grids, blocks, threads, or sort of grids, work groups, work items. The hardware is then free to schedule the work as it sees fit. This is now the basis for a scalable architecture that we can use to do large quantities of work. So there's some more documentation around HIP on the ROCm web page. We're currently using on ARCHER2 version 5.2.3. We're a little bit behind. This is a limitation of software versions we're on. But those are the relevant docs to look at. Get up the next section. So just before we break for lunch in the next half hour, we'll break for lunch at 12 o'clock. What I'll do briefly is I will look at section on HIP programming. I'm afraid at the end of my nice slides, and I'm going back to the older course materials now. Discussing HIP programming. The example at the end of this is to discuss how to move data between the host and device. We should have time to work on this problem for lunch. When we come back, we'll maybe look at a solution, and then we'll move on to writing some kernels this afternoon. So we've already looked at this model, this diagram before. Actually, before I jump on, are there any other questions people have about what we've discussed this morning? Silence. Excellent. Good. Right. Please do ask any other questions you might have then. So what we're going to mainly consider ourselves first is around this moving data across. We can't execute the kernel, anything useful, unless we can get data to the GPU to operate on. So we're going to focus on the operations to move data around. I'm going to zoom in a bit here so it's a bit more visible. Better. Okay. Yes, so we're talking about moving memory between host devices. So what do we need to include? What do we not need to include? As a standard C++ source file, needs to include the HIP runtime. Okay. I'm getting told my connection's a bit flaky, so if I'm dropping out, my video's bad, please just message in the chat and I will wait for it to recover. But everything's coming fine back to me at the moment. So yes, you need to include this HIP runtime, so you can compile programs with HIPCC. There is also a subset of this runtime available as well, which does not need to be compiled with HIPCC. So this is all the sort of host code bits. So memory management is the key thing we're going to focus on to begin with. Data accessed by kernels must reside on device memory. This is sometimes also referred to as global memory. Also, device global memory or global memory. I think device memory is better. There's different ways of managing the allocation of movement data between host and device. Broadly, explicit allocations and explicit copies, or the use of managed memory. We'll come on to managed memory later, but to start with, we're going to discuss explicit copying. Declaration is of our standard C++ types and pointers. So I'm on the host, I'm going to have a double, in this example, pointer data, initialize it to null, doesn't have a location yet. I'm then going to call hip malloc some size to give that pointer a location on the device where some data can be stored. After doing some work sometime later, I'm going to have to remember to free that data. So this is not very C++y. I don't have a constructor or destructor that's going to do this for me. I'm going to explicitly remember to free the data I've allocated on the device. And if I don't, I'm going to use up my device memory. So these are host pointers to device memory. This is a really important concept. They have value, but they can't be dereferenced on the host. You get a program error because the memory location doesn't exist on my host. We also want to do error handling. So hip calls path back an error. In the examples you're given, there's a macro that helps to handle this. This is one of these little chunks, code snippets, that when you're doing this, I would just copy this and keep this around for your own programs. Having a nice macro to collect and test these is important. So memory movement. We're assuming we've established some data on the host, and the copies to the device are via hip mem copy. So schematically, this is I have some data, which is my destination, my pointer to my device memory location. I have a pointer to some data on my host. I have the size of the data being moved. And I have a kind of, they're referred to as kinds. There's a hip mem copy kind that tells you the direction. You can set these kinds up as separate values and pass them in. So if you've got a lot of common movements in a single direction, you can alias them nicely and things like this. It's because these are quite long to write out every single time. Hip mem copy host to device will move the host data to data. We can then do something on the device, operate on the data we passed in to the kernel, and then we can move in the opposite direction. In this example, we're moving back to the same location. We copied information data from the host to the device. We don't have to do that. We can then copy the data that's on the device to a different location on the host. We're entirely free to choose. But the syntax is the same. It's hip mem copy destination, source, size of movement, direction of movement. And in this case, we switched around. So now we're doing hip mem copy device to host. These are blocking calls. They will not return until after the data has been stored in GPU memory or an error has occurred. And then here's a formal definition of the API interface. So we need to talk a little bit about error handling. Most HIP API routines return an error code. It's really important to check this value against HIP success. And if an error occurs, this can be interrogated and give you some meaningful information about what's gone wrong. So you have HIP error name, HIP error string to get some useful description of what's happened. There are obviously debuggers that allow you to help to do this, but having the ability to test these is quite useful. So we often have a macro. There's been one set up in the example files for this. So to avoid clutter, we omit error checking in the example code snippets we provide in the text, but in the example files, they are included. Yeah, so this is, remember, because you're doing this across two different devices, it's really important to check these errors as you go. Same as you'll often advise with MPI calls to do. Right. With that said, we now have a first exercise. So we're going to do this up until lunch. I know it says 20 minutes, but we're basically at 12 o'clock in 20 minutes. So we'll do this for half an hour. When we come back, we will discuss the result and answer any questions. Well, answer any questions during the next half hour. So we're going to look at the associated exercise within the documentation. So I will just link this. So in the chat, for anyone who hasn't found this already, there's the course, GitHub page. So 1 second. Okay. And here's the section on this particular example. Got this right. Yes. Okay, so you will need to log into ARCHER2, make sure you've moved to the work directory, which looks something like now. Yes, right. Okay. My login's gone off. That's fantastic. But if you go to ARCHER2 and you log in, and you should get confronted with a splash page. Your present working directory will be your home directory. So I've given myself an unhelpful username because I run out of things to use, username to use. To the work directory. Chat for those who forget. Bigger. And you'll need to do a git clone here. And you can go to the course, and we're in section 2.1 for this exercise. Then there's an exercise file, a submit script. You will need to add in this account, or you'll need to pass this account into, I think it's sbatch minus capital A and then the account number if you don't. This is set up to run for you anyway. It's going to run something called ROCm SMI initially. This is good at detecting, probing information about the GPU, its state, whether it's running, information about it. So if you get done very quickly with this and want a little exercise, try to run this with a few different parameters so you can understand how it's working. You will be provided with the exercise file in here, which has some instructions about what you need to work through and what you need to add. But first of all, read through it. You will need to load, to be able to do the compilation, you'll need to load some modules. So we're going to use the program AMD as we said. We'll need to load ROCm so we get access to the compiler we need for the GPU code. We need to load this Cray P accelerator AMD GFX. This is some Cray HPE magic, which is setting the compute capability for you as an environment parameter. We're doing this also for the CPU because the CPU has changed between the login nodes and the GPU nodes. So it's as opposed to AMD ROM chips. We can compile with HipCC, or we can use the compile wrappers and use CC capitals if you want. But the documentation tells you what to do, and you want to initially to submit to the queue and see what happens, and make sure that you're getting it working and completing, but with the incorrect results. It will tell you whether you're getting the right answer. I want you to sort of work through this. Up at 12 o'clock, I'll be here to answer any questions. We will then jump back in at 12 to take a break, and we will be back at 1 o'clock after that. But please ask questions as you work through this on ARCHER2.
I know different people are different stages of this, but at least one person has got towards the end. If you do find yourself getting through this quicker, start to look at things like what information you get out of device properties. Maybe try to write your own separate file from scratch and just probe information about the device available and see if you can establish some of the hardware stats about the device compared to what you find in the documentation. The other thing is to look at different types of the kinds of memory copies that you can have. So HIP talked about host to device and device to host, but there may be some additional ones that you could look into as well. So a couple of questions in chat. I'll come back to you, Paul, in a minute. Matthias, so what is the use of memory copy device to device or memory copy host to host? So if you have multiple GPUs on the same node, you don't know if you need to do this MPI or not. The other issue here may be because on stuff like the MI250X, you have 2 GPU units on the same device, and you want to copy between them. So they might enable that without explicitly needing an MPI call. Or you may want to move data between 2 locations on the same device, things like that. Well, if both locations are valid, the movement isn't an error, though, is it? I'm missing some of the own instructions here. Yeah, if you've got uninitialized memory in a location, but you've got a point to it. Yeah, that's what I'd expect, right? You've got to be careful with this because you've got some uninitialized memory location, which is just going to copy values from the device to host, but the device was never initialized. So if you get this wrong, then you can have problems. So yeah, it's not strictly an error though, because the operation of movement is completed correctly. Yeah, this example doesn't explicitly do operations on the device. This is about data movement. This is the next example. We'll start looking at kernels. No, I'm trying to, sorry, I'll go back to Paul's thing. We will discuss how to then set up kernels in the next section. This is making sure you understand how to get data available to you on the device to do stuff. Coming back to Paul, yeah, I think I'm trying to remind myself, if I'm totally honest, on the fly. I think that's what it's meant to happen, and that's meant to be the point. Oh, I see. Yes. I'm sorry. That's a good point. It's undefined behavior. Yeah, I should have read the docs. Sorry. Thank you, Ian. Okay. That's lunchtime. We'll restart at about 1 o'clock. We will then move on to the next exercise. This builds on this data movement example. The 2 things we'll cover this afternoon are
Let me just check. So first we'll look at executing a kernel and give an example with the kernel function actually doing something. It's going to do something very simple, but it will do something initially. And then we'll look at how we can drive occupancy and get performance. I still think we're probably going to be done at around 3 o'clock. I think we just way we've reorganized this left us a bit of spare time in the afternoon. So we'll probably now say we'll do an hour from 1 till 2 o'clock, have a short break, and then do an hour from around 2 o'clock onwards to 3, and see how we go. And maybe give you a little bit of time back at the end of the day. Okay, I'm going to log off now for an hour, and I will see you again at 1.